Okay, hello, good day. My name is Benedict Byrne. I'm an antenna engineer and I'm part of TechEFA, so the antenna section at ESA ESTEC. I'm the CubeSat activities coordinator of the section. So this is why I'm going to present today the activities that we're having in the section regarding antennas for CubeSats. So here's an overview of what I'm going to present in the following slides. So I'm going to give a short introduction on TechEFA and also on CubeSats in general. Then I'm going to present the activities we are having. So I grouped the activities into three categories. So first of all, the CubeSat antenna developments. So these are basically ESA R&D activities in the frame of ARTES, TDE, TRP, NAVISP, etc. Then I'm going to present the CubeSat mission antenna support. So where we are giving support to ESA CubeSat missions in the frame of GSTP Element 3 Fly with supervision of Tech SPC. And the third category is on CubeSat antenna measurements, where we have been doing measurements on CubeSat antennas in our anechoic chambers at ESTEC. So in this case, the compact antenna test range and Hertz facility. Then at the end, I'm going to give a summary of the activities in the form of two tables with regard to frequency bands and gain levels, as to give a nice overview of all the activities we're having in the section. So first of all, a short introduction on TechEFA, so which is the antenna and sub-millimeter wave section. So we are giving technical support and consultancy to ESA projects, programs, and general studies in the field of space antenna systems, sub-millimeter wave instruments, and associated technologies throughout all project phases. So as you can see in the figure represented on this slide, the fields we are active on are navigation, science, Earth observation, telecom, but also other fields such as CubeSats. And so this field is actually growing extremely rapidly, so which will be reflected in the, as you will see, in the high number of activities we are having in this field. So I will not have much time to go into details of each of the activities, but I'm trying to give a flavor on what we are doing in this field. Then what are CubeSats? So CubeSats are small satellites of standardized external cubic unit dimensions. So 1 unit equal a volume of 10 by 10 by 10 centimeters. And these CubeSats are launched inside a container. The first CubeSat concept dates actually from 1999. So here the goal was to give students a practical and cost-affordable experience of space exploration. And since then, the CubeSats are growing in size, complexity, and cost. And there has been a transition actually from educational tools, so from smaller CubeSats, 1 to 3 units CubeSats, so up to 10 kilogram CubeSats, to technology demonstrations or even to operational missions. So it's today we are even having CubeSats of 16 to 27 units. And so in the graph on the right, you can see that the launches of the CubeSats have grown exponentially. So today we're having more than 1,700 CubeSats launched. So now let's go to the activities we're having in our section. So this is the structure I'm going to present the activities. So always 2 activities in parallel. They're not necessarily related, but I try to put the ones together that are more related. So on the left, you are having an activity on verification and calibration techniques for low frequency antennas. So here the objective is to come up with new testing techniques as to allow large antennas working at frequencies between 20 and 400 megahertz, so very low frequencies, to be tested in the Hertz facility. The first customer here will be the Juventus CubeSat, which is a 6U CubeSat and daughter to the Hera mothership. It is planned to perform asteroid research on Didymos using the low frequency radar. So an antenna that is similar to this low frequency radar is subject of the following activity. So on tubular deployable antennas. So here the objective is to develop an antenna working at 25, 50, and 100 megahertz for ground penetrating radar and for small planetary missions. So the deployable lambda half dipole at, for example, 25 megahertz will have a length of 3 meters for each arm. The next activity is on the IAS miniaturized antenna. So IAS standing for Automatic Identification System, which is a maritime tracking system, and that is working at the VHF band around 160 megahertz with a bandwidth of 25 megahertz. So here the objective is to develop compact multiple beam deployable array antenna with the goal to enhance the detection ratio. So the antenna that has been developed is a compact cross dipole, as you can see in the picture, over an AMC ground plane. In the following activity, the subject is an antenna integrated on solar panel. So the objective is to develop an innovative off-the-shelf panel integrated antenna product that will address the telecom and power needs of pocket cubes. So pocket cubes being cubes of 5 by 5 by 5 centimeter volume. The antenna here, as you can see on the picture, also is a N-Fi antenna, and more precisely a printed Yagi UDA antenna. The next activity is on an all-band GNSS antenna. So here the objective is to develop a receive antenna for precise point positioning, so PPP application, in multi-frequency and multi-constellation environment. So the aim was to cover all the GNSS bands, so Galileo, GPS, GLONASS, and Beidou, plus the Inmarsat L band, and to fit on a one-use surface. So this activity has been actually successfully closed, and an FM is available and is represented here on the picture. Another activity that has been successfully closed is the next activity. So the receive and transmit S-band antenna for CubeSat. So here the objective is to develop a wide beam S-band antenna for TTNC and PDT, so payload data transmission application, with low-cost production. This antenna has been successfully closed, but also is flight proven since it has been launched and is working since last year. The next two activities, are actually two parallel contracts on the topic of deployable reflector antenna for CubeSat. So here the objective is to develop a large offset fed reflector antenna with a diameter between 1 and 3 meters and working at frequencies up to Ka band. And the aim is to manufacture and test the reflector breadboard up to TRL4. The next activity is also on deployable reflector, but this time for millimeter wave frequencies, so above 50 gigahertz. And the reflector diameter should be between 0.5 and 1 meter. And the aim is also to go up to the technology readiness level of TRL4. The activity on the right on cost-effective high-gain CubeSat antennas. So it's an activity on a mechanically scanning antenna, so mechanically scanning in elevation and azimuth. And the antenna should be working at frequencies up to 60 gigahertz and for intersatellite link application. And it should fit in a volume of smaller than 0.5 U. The following activities on the deployable helical antenna. So the objective was actually to develop two types of deployable helical antennas. So the first type being an antenna working at frequencies between 860 and 900 megahertz and fitting into 0.5 U, and the second type being an antenna of working at 400 megahertz and fitting in 1 U. So two antennas of the first type, so at 860 megahertz, are currently flying with Lacuna Space, so since 2020. On the right, we have an activity on flight representative reflect array. So this antenna is similar to the one also flying on Marco, so developed by NASA JPL. So it's a patch array feeding a deployable 3-panel reflect array, and it should be working at X-band. So this antenna is planned to be flying on GOMX5 and Margo. And so this is a good transition to the next slide and to the next activities following, where we have been, or where we are giving support to CubeSat missions. So first of all, sorry, the GOMX5 CubeSat, which is a 12U CubeSat, and it's showcase of new CubeSat capabilities, especially on high-speed communication links and high levels of maneuverability. The satellite should be equipped also with number of advanced communication technology payloads. So on the antenna level or antenna side, these are an X-band reflect array, so which I just presented in the slide before from the GSTP activity. Then the GNSS antenna from the Navisp Element 1 activity, which is an option. And we are giving, or we have been giving support and are still giving support on the TMTC S-band sleeve antenna. So this CubeSat is expected to fly in Q2 of 2022. Then Margo, which is standing for Miniaturized Asteroid Remote Geophysical Observer. So it's a 12U CubeSat, and as the name says, it will observe an asteroid. So the goal is to go beyond Earth orbit, and it's planned to spend around 6 months surveying its asteroid target with multispectral imager and laser altimeter. And then the data will be returned using the X-band reflect array from the GSTP activity presented in the slide before. So the launch is expected here for 2024, 2025. Then PRETTY, standing for passive reflectometry and dosimetry. So the reflectometry, there will be a patch array used working at L5 band. So it went from L1 to L5 as to give better scientific results. And actually this will be the first CubeSat to exploit GNSS-R at L5 band. Here the launch is expected for 2022 on a Vega SSMS. Then RACE is standing for Rendezvous Autonomous CubeSat Experiment. So here the objective is to demonstrate feasibility of rendezvous by fly together in close formation, but also by rendezvous and docking of these two 6U CubeSats. The launch is expected for 2024. And then two CubeSats where we have been giving support and that are currently flying. So they have been launched some weeks ago, so in August of this year. So namely RadCube and Sunstorm. RadCube being a 3U CubeSat, and with the objective to measure space radiation and magnetic field in LEO for space weather monitoring. And Sunstorm being a 2U CubeSat, and the objective to measure solar X-ray pulses produced by coronal mass ejections with X-ray spectrometer. So as mentioned, they have been launched and LEOP has been completed, and currently the commissioning is ongoing. And for Sunstorm, the first solar X-ray spectrum has been already transmitted, and so you can see the result in the graph on the right. Going now to the measurement activities on CubeSat antennas. So we have been measuring the antennas, so an S-band patch and an X-band patch antennas of the Proba V companion in the compact antenna test range. We have also been measuring the antenna on Carmen, which is a 3U CubeSat and which has been released from the ISS, and that was falling direction Earth to gather data on physics of reentry. So as to return the results of the experiments, this CubeSat has been using Iridium commercial ComSat network, and so the antenna to do so has been tested in the Hertz facility. Then two Hyper CubeSats, so Hyper 2 and Hyper 3, 6U and 3U CubeSats respectively. Some antennas have also been measured in the Hertz facility. And these antennas are represented or written down on the bottom of the slides. And then EARSat 1, which is a 2U CubeSat and part of the Fly Your Satellite program, which is managed by ESA Education Office and is in close collaboration with universities. So here also two antennas, so a VHF dipole and UHF dipole, have been measured in Hertz. And last but not least, the Fraunhofer GNSS antenna has also been measured in Hertz. So now coming to the summaries. So first of all, the summary with regard to the frequency bands. So first of all, I want to mention that. So I went quite fast because of the time through all these activities, and actually I didn't like there are even more activities that we're working on antennas on CubeSats, but which I didn't show because of confidentiality or other reasons. But we can see here on this table that actually with the activity already that we are covering on pretty much all frequency bands of the microwave range. So going from VHF, UHF, L, S to X, K, and W, KA and W band. And so I represented the ongoing or successfully closed R&D activities in yellow, and the more advanced CubeSat missions, so that have been tested in our facilities at ESTEC, or where other mission supports in green. And then the second table with regard to the gain level. So here I did a separation between low, medium, and high gain levels. And again, we can see that there's a nice distribution of the activities over the different levels of gain. So in green, I added also the antennas that are in orbit or have concrete flight opportunities. So as to show that there is a real interest and that the aim of these activities is to fly the antennas at the end. And I also want to mention that we managed always to maintain the timeline of new space, which, as you may know, it's going all very like it's going all quite rapidly. So here I want now to give a special thanks to my colleagues from the TechEFA section for helping me preparing these slides and also giving me the relevant information so that I was able to do this presentation. And I want to thank you for your attention. And if you have any questions, I'm happy to answer them. Thank you.